Recording in progress.
Awesome. All right. So, differentiation rules. So if we remember, we know the derivative is this, the limit as h approaches 0 of f of x plus h minus f of x all over h, right? You need a pencil? Here. Pencil. Oh, someone need a pencil? No? Right. All right. Anyhow, but also we know if you have a constant, we actually could just not really waste our time kind of doing this. Because I mean, if you think about it, right, if I plug in x plus h, what am I going to get? 7. And if I plug in f of x, what am I going to get? 7. What's 7 minus 7? So what does that all become? 0. So analytically, we see why it's 0 using the formal definition or the limit definition derivative. But graphically, that would make sense too, right? Because what's that graph look like? Just a horizontal line. What's the slope of this? 0, right? Also think about numerically. Just 7 the whole time. Is there any change to it? No. It's a constant. So whenever you have a constant, f prime of x is always 0. Just so you know. You don't have to waste your time doing the whole limit thing. I mean, I did just to show you quickly. Just 0. That's all. So we could just assume that, right? Okay. So, and be really kind of honest, we're not going to really do this too much anymore. I mean, it's good to know every once in a while, kind of bring it back, but yeah, you don't really need to worry about it. Okay, 2. 2 is a linear function, right? If you think about it, just a line. What's the slope of that line? So what's that prime of x going to equal? 1. There you go. This is true for any line. For any line, just take the slope. That's your derivative. That's it. Now, this one we already know. I'm just going to kind of write them out. We just know what's happening. I'm not going to work through it again. That's 2x, right? And if you think about it graphically, before on the left side of the parabola, are the slopes positive or negative? On the right side, positive or negative? Think about if you plug in a positive into 2x, positive. Negative, that negative, right? So each of the lines, the slope of those lines will follow that formula, 2x. 2x represents the slope of all those tangent lines, right? This one is also pretty easy. We've seen this one. Remember that one is 3. Yeah, and what does x cubed look like? If I draw each of those slopes, are they all positive or all negative? Yeah, except for at 0. Because it'll flatten out. But then it gets steeper afterwards. By the way, it's also kind of interesting because if you see the slopes initially, they're pretty steep. And they get less steep until it hits 0, and then they get more steep afterwards. That's a phenomenon called concavity. I don't think we'll get to that. I'd love to get to that if we can. We have some time, maybe after sequences and series, we will talk about calculus again, but concavity is a measure of how fast the derivative is changing. So it's like a second derivative. So, but we won't have that discussion, unfortunately. I don't think we will. For problem 5, if you see the pattern, I think we kind of gather that this will be what? 4x cubed. If you were to work it out, you have to expand it like crazy. Because I'm just going to set it. I'm not going to do it because I don't feel like it. I don't think you guys want to do it either. Unless you really want to. No? Okay. So I think the room doesn't want to do it. Okay, that's good. But do you see why you have to expand x plus h to the 4th power? And that's going to be kind of nuts, right? Because you have to boil that so many times and then take those derivatives. I'm sorry, then clean it up. And then, of course, simplify and you get 4x cubed. But I mean, I don't think it's necessary. We don't need to do it. I think you get the idea. So this leads us to the power rule, or one of the shortcut rules. So essentially just says this. If you have x raised to the n power, it has a power function, mind you. You do not do this for exponential, by the way. Please, please, please do not do this for exponential functions. Like if you have 2 to the x power, can't do it. It's only going to work for power terms where x is the base and the exponent's a constant. Very important. The exponent must be a constant. This is only for power terms. There's actually a formal proof. I don't know if we'll get to that. We'll see if we do. Only for power terms, meaning the base is x, the exponent is a constant. Very important. So it's just this, n times x raised to the n minus 1. So you move the exponent to the front, drop it by 1. Yeah, oh, go ahead.
Would that work as well if it was like square root x, because you could do x to the 1/2?
Correct. Yes. That's a great observation. This will definitely work for radical functions, 100%. Assuming it's just x inside. All bets are off if it's something else. And that's another rule called the chain rule, which we'll talk about our last unit, I think, next week. Really good. Correct. And that's a constant multiple. That's the next thing we'll talk about. So you're a step ahead of us. That's rule 3. And if you have this notation d dx, remember that's just a derivative operator. D dx is just an operator for the derivative. You've seen it in the calculator already now. We hit in deriv, it shows d dx. You know, if you see that, you know, you're doing the same thing again. And I will say this, I have several friends who are my age who still remember this, who have nothing to do with math in their careers. They still remember this from 30 years ago. It's one of these things that kind of just sticks because it's a nice rule. So for example, problem 6, what's that going to be? Yeah, because if you did the limit definition, you guys would kill me. That'd be crazy, right? I wouldn't make you guys do that. For 7, yeah, you push the 11 off to the side, kind of like this, and focus on the x4. The 11 comes along for the ride. Yeah, so it's very simple. It's a constant multiple. You can do that. You're allowed to do that.
By definition, f prime x.
That means doing the long way. I don't want to. I don't feel like it. You could. I just don't feel like it. It's just to prove to you. I mean, I'll show you the filled out notes really fast. Which I think I have in Schoology. I don't know. Let's see. Lovely. This is like when I was teaching during the pandemic. That was insane to teach this on Zoom. And they rushed it too. They actually literally made me teach the second semester in 4 weeks. Yeah, around this time 4 years ago. That was absolutely insane. Yeah, so only like 2 classes met every 4 weeks, and you had to cover the entire semester in those 4 weeks. That was the dumbest thing I've ever. What was that? No. So basically every class met for like 3 hours a day, Monday through Thursday. So you had like your A period Monday through Thursday. So you had A period from like 8 to 11 on Zoom, and then you had a lunch break, and then from 12 to 3 you had your B period class, and you did that for like 4 days in a row for 4 weeks.
So twice a week for 4 weeks.
Yeah. Well, no, you had 2 classes. Yeah. So I had to cover anyway. It was. I don't want to get into it. It's just too. It makes me upset. So it was crazy. And then we kind of reopened the campus afterwards. But anyway, if we want to see the formal definition, it looks like this. So if you were to go through it, but I'm not going to because you guys get the idea of what to do. So we'll just move on.
So do you just like forget about the constant to the end?
Correct. And x to the 4 looks like this, if you were to work that out, which again, I don't want to do. So we'll keep moving. So to what Olivia brought up a few minutes ago, when you have a constant, just goes along for the ride. So, and if you use a function in terms of x, you could write like this: c times u prime. So that's all. So u prime represents the derivative of u. That's all. We do use the letter u quite a bit for substitution. Kind of get used to that. It's really bad for me because my handwriting stinks and my u's and v's sometimes blend. So I'll try to be as detail oriented with my writing. I apologize if it blends in.
The ladder's the most.
Get it. Yeah, right. So this one here, again, we know it's going to happen. It's 1/5 times what? Yep, that's it. Or if you want to clean up just a tad, you can say 7/5 x6. Yeah. So it's always pretty easy stuff. Another rule, sum and difference rule. If you're adding a bunch of terms, power terms, mind you. Well, actually, we'll get to other stuff like trig, and I don't think we'll get to exponential functions. But if you have a bunch of terms being added, just take the derivative each of them individually and add them up. That's it. So if you have x42 plus x93, that's going to be 1/2 times 4x cubed plus 1/3 times what? And if you want to clean it up, you can. If you clean it up, it should look like this: 2x cubed plus 3x8. Not that hard, right? Let's try next one. What do you guys think next one's gonna be?
30x squared.
30x squared, 12x plus 5. And what about 13?
It doesn't.
Don't worry about it. Yep, it's constant. Don't worry about 13. It goes away. If you want to put plus 0 for the 13, go ahead. But that's good enough. And if you were to do the limit definition of the derivative, that'd be crazy, right? For 10a. I would never even ask guys to do that. So we have the shortcut rules because we want to be efficient, right? Now, the equation of tangent line, that shouldn't be so bad. Remember we lean on point slope form? And what's the slope? How's the slope tied to all this stuff? How do we express the slope? Or where do we get the slope from? From the derivative, exactly. So if you think about it, bless you. I should probably figure out what f of 0 is first. What's f of 0? No, f of 0. 13. What's f prime of 0?
There's no slope.
That's 5.
This is differential.
So when you work this out, it's going to be y minus f of 0 equals f prime of 0 times x minus 0. And what's f of 0 again? What's f prime of 0? So you get that.
Wait, so number 10. What you that 5x? Is that just like when you put in the derivative? Is that just become 5?
Exactly.
Oh, and then 13 because the number is just totally 0.
Right. Yeah, so f of 0 is 13, obviously. F prime of 0 is 5 after we're full derivative. When you do the equation of tangent line, the slope is the derivative. And the y value is, of course, the y value plugging 0 for x.
Got it.
Yeah, so when you do equation of tangent lines, just lean on point slope form. It's way easier than rewriting it in slope intercept. Don't do slope intercept form. Actually, doesn't have much of a place in this class, so don't really worry about it. Just, I mean, you can if you want, but it's not necessary.
Okay,
What's that?
where does the 13 disappear?
Disappear?
In 10a. Like, why is there no 13?
Because it's a constant. What's the of
There's
constants?
extra slope.
Well, what's the
yeah,
slope of
yeah.
13?
There's no slope.
There's no slope, 0. Right.
Oh, and there's no derivative of like f of x equals 13, so you just add. Yeah.
Yeah, 0. Right. You don't worry about it. These are good. Yes. Yeah. So the tangent. Sorry, the tangent line is just the derivative. The slope of the tangent line. So if you have like this crazy curve, right? Actually, this will help. I think you're looking to visualize it. So here, don't worry about the recession. Trump's screwing up our country. Just to save money. Save money for a rainy day. All right. So anyway, 10x raised to the 3rd power minus 6x squared. What was it again?
Oh,
plus 5x plus 13.
Slope from the F time. which
Okay,
is on
and the derivative is this, Easton, right? Y equals 30. Actually, our tangent line. Let's do that. Y minus 13 equals 5x. So if I clear my screen for a moment,
uh, what is that?
because it's really hard to tell. It actually is a tangent line.
Oh.
So
And then
it does have
and it's
some
also
kind of weird curvature. So it's,
No,
it's
the
actually
slope-
touching the curve at just
sorry.
one point.
No, X1.
That's what a tangent line represents. Is that your question? Okay.
Oh, yes, okay.
Let's keep moving.
Like the derivative where you can like solve like each part individually, like for that one,
Mhm.
do
Yeah.
derivative 7 and then.
Yeah.
add that. Okay.
Yeah, that's some difference rule, essentially. Okay, horizontal tangents, guys. What does that mean? What's y prime equal? 0. So let's do it. So 0 will equal my derivative. Cleaned up. Now, all those years, like in middle school and beginning of here, we made you do all this factoring. Why? Because of this. We want to make sure that you can solve these things because you're going to do some other applications, not in this class, unfortunately. I really love doing more applications like this problem called like optimization related rates, which are fantastic calculus problems, actually very practical problems, like actually using real life applications to, prove why certain things work the way to do. And you have to do some factoring afterwards. We won't get to those applications, but we'll do some problems that involve factoring. That's why we spent all these years doing that, because it should be pretty natural. What do I factor out, guys? Yeah, you should be able to do this in your sleep. Actually, this is my eyes closed. I'm just kidding. X plus 3x minus 2. Right? What does x equal? So what does that tell me about the graph? At these 3 points, what's happening on this curve here? At 0, -3 and 2. Well, so what does that mean in terms of like the feature of the graph? Like what's special? Not so much that, but it's gonna be the highs and lows. Wouldn't it be the peaks? Because think about it, when you hit a peak, what's the slope of the tangent line there when you hit a peak? It's horizontal, right? If you have a peak to as a graph. So if I were to graph this,
Or Mr.
Mhm.
How do we know their peaks? Because aren't they all degrees of?
great question, because it could actually just flatten out and keep rising. That's something called the first derivative rule. Sorry, the first derivative test, which we won't do in this class. You will pick it up when you move on to BC next year. I really wish we could do that. It's something called the first derivative test, because you have to show, hey, is derivative positive or negative beforehand if it's a min or max. That's a great question you brought up.
Oh, because that's just the derivative.
That's derivative. We don't, but it can provide that information.
So no, I was confusing it with like the actual. Like,
So plus, yeah, let me just show you 4/3 x cubed
Time to go back.
minus 12x squared plus 7. Okay. So if I clear screen for a moment, you see that there's a high point there. See there's a low point there. So before, when you graph polynomials, you were just doing m behavior and x-intercepts and y-intercepts. You didn't really know where the highs and lows were. Now you can find that because you know about derivatives. Right. You see, it expands your horizons here. Like, see, there you go. Now I know how low it goes, right? Yes, local extrema. That's what we call it. Right. And you'll basically do a lot of this in the fall. A lot of this stuff in the fall. And there's applications that go with it as well. So it's really neat stuff. But for now, we're just finding the x coordinates where it happens. So, yeah. Okay. Next rule. This is a big one. I'm going to take a little time because I want to rush it. Product rule, quotient rules are 2 big ones. And then we're just kind of talking about power rule again, especially when exponents are negative or whatnot. Some other wacky problems, multiple derivatives, and how to use a graphic calculator. So we should be able to wrap all this up in about 15 minutes. Okay. Product rule. So the product rule states this. If you have two functions being multiplied together, you can multiply it out if you want. Sometimes you can't if it's a weird expression like tangent or whatever. But if you have a bunch of polynomial expressions that are being multiplied, you could use this rule instead of actually foiling everything and doing the power rule for each term. So I like to think of it like this. UV prime is U prime V. I told my U's and V's blend in. UV prime.
I don't understand why people were.
I don't know.
With the exact same.
Let's do A and B. Okay, whatever. But what it's saying is that I can take the derivative of one function times the original of the other, plus vice versa. Plus the original of the first times the second. So let's look at this one here. So we know, so we're asked to find the derivative f of x, right? And what's going on with fx? You have this, which I'll call u. You have this, which I'll call v. So when you want to find f prime of x, it's going to be u prime times v plus u prime. Yes, for u, it's going to be power rule. Oops, sorry. So let's start with u. What's the derivative of 4x squared plus 6? 8x. And tan times tangent x. Plus, what's u originally? Okay, I've not taught you guys how to derivative tangent yet, or derivative trig in general. We'll do that actually next week. The derivative secant squared, derivative tangent x secant squared x. And you can leave your answer like that. You do not need to distribute or do anything else. Leave it like that. 9% 8x tan x plus 4x squared plus 6 in parentheses times secant squared x. That's the product rule. If you want to prove it, I could actually come up with like a couple of nasty polynomials and foil them and then do the power rule for each term or do the product rule. In the interest of time, I'm not going to do that because we're going to see a lot of these later on. But that's the product rule. Quotient rule. Quotient rule is a funny one. It looks like this. I know it looks a little daunting. Here's how I like to think of it. U over V prime. So it's going to be this. U prime V minus UV prime over V squared. And it's actually kind of so there's a little kind of like rhyme with it. I would kind of say this. I think if I get it correctly, low D high minus high D low.
Are we gonna have to memorize these?
No. Over low squared. And away we go. I know it's kind of lame. No, not really. But low D high minus high D low over low squared, away we go. Okay. So low D high minus high D low over low squared, away we go.
That actually makes sense.
What?
So it's just a funny rule because there's so many things going on with it. But essentially, you're doing the derivative of the top times the bottom minus the reverse divided by the bottom squared.
How did like anybody figure these out?
I don't know. Maybe Sir Isaac Newton or I don't know, or Euler. I don't know. So if you want to take this derivative, we'll let x cubed be u. We'll let x squared plus 2 be v. So I'm going to do x cubed prime times x squared plus 2 as is minus x cubed times x squared plus 2 prime over x squared plus 2 squared. What's the root of x cubed? 3x squared. Ah, geez. What's the root of x squared?
2x.
2x, and the bottom is what it is. To be very honest with you guys, I do not care if you simplify this. I really don't.
Wait, where did two
Should
go?
we talk like tests and stuff?
Derivative, dude. What's derivative 2? 0.
Oh. But, wait, no, never mind.
Yeah, well, I did a derivative of the high. Right, which was x cubed. Sorry, derivative of x cubed 3x squared. Times x squared plus 2 minus reverse. Now, if you want to clean up a little bit, sure, that's 3x4 plus 6x squared minus 4x to the 4 power. I guess you could clean it up. Don't bother foiling this, because you just make it worse. Why would you want to add more terms? I don't know why, I don't care. But why do we have this? Because ultimately we're going to be finding horizontal tangents for these, right? So sure, maybe then we do want to clean up the top. Or we're going to do some other things, other applications of this down the road. For now, I just want you to go through the mechanics of like, oh, okay, here's what I have to do. Simplification, I really don't care. Because it's not really, you guys have spent years and years simplifying, so I don't, it's immaterial to me. I mean, on the AP exam, if it's simplified, then sure, do simplify. If it's multiple choice. I mean, if I were to simplify, it look like this. Negative, sorry, x4 plus 6x squared, is that correct? If you were to simplify, I think it would look like that. Am I correct in saying that? I think so.
Maybe.
Yeah, maybe. I will tell you, so if you do simplify and it's wrong, you'll miss a point though. So just don't do it. You don't have to. Right? So, all right, let's keep moving. All right, here. You could also do quotient rule again.
Could we just do x to the minus 5?
We'll get there in a moment, yes. So if you did quotient rule again, so it's 1 prime x5 minus 1 times x5 prime. What's the root of 1 prime?
0.
0. What's the root of x5
5x.
over x to the 10 power? So what do you get? Negative 5x4 or negative 5. So you could do that. Can. Or this will lead us to what we see on the next page. Before I do that though, before I show you the other way to do this problem. Does that make sense what I did? What was my numerator? What was my denominator? 5. Just low D high minus high D low or low square, way we go. So 1 prime 0 times x5 minus 1. Derivative of x5 is 5x4. Of course, that's x to the 10 power. This is I do want to clean it up, so I want to show you the alternative way, getting you the same thing. If I do the alternative way, isn't that the same thing as x? What Ollie said, right? Is that the same thing? At 1 over x5 is x to the negative 5? And why do we spend all those years talking about rewriting exponents for this moment? What's this derivative going to be? If I use the power rule. Isn't that the same thing as what I just got in Brown? Yeah, 100%. Same thing. I think what I did in red is much easier. So sometimes there's a fine line as to when you should really be so particular about the quotient rule, or just if it's, if you could rise a monomial, which I did, x to the negative 5, great. Just do that. So the bottom line is you can do this power rule for whatever the exponent is, as long as it's a constant. So I'm just repeating what was on earlier in his notes. That's all. So it doesn't have to be a whole number, right? It could be a negative integer. That's fine. And by the way, it could be a fraction too. If we have like a radical x to the 1/2, like a square root of x, you do the same thing. Because now we know, because you guys remember this, we had root x. What was that derivative? That was 1 over 2 root x, right? But what's root x as an exponent? And what happens if I do that power rule? Where does 1/2 go? To the front. Drop it by 1. Isn't x and a 1/2 1 over root x? Yeah, times 1/2 on the bottom. So we see that this rule just saves us so much time. Do you really want to do the limit definition for this over and over again? No. For any radical? No. Remember we had to do the conjugate, all that work? Why? Switch to the rational exponents, do the power rule, done. Much easier. So let's look at these here. So what do you think is going to happen? Well, before I do that, let's just let's prep it. Does that make sense? So it's probably going to be plus 18 x what power? Nope. There's 7. Basic arithmetic, guys. Gotta be careful. If you want to write like this at the end, go for it. I don't really care. This is fine also. Either way is fine.
Yeah.
That's because I'm going too fast. And you guys are paying attention. So thank you. I saw some confused looks. Okay, we feel better now? Okay, good. Sorry. Sorry about that. 14x6. Okay. Problem 16 is kind of funny. So this will be what? 7 u prime minus 3 w prime. Ooh.
I'll make it multiple.
Great question. U and W are their own separate functions. How are U and W combined here? So what will that be? Product. What's product will U prime W plus 2W prime. And then you substitute the values that are provided. So it's 7 times -1, because all we're plugging 5 in, minus 3 times 3, right? Minus 5 bracket -1. Oh, bless you. Plus 10. Just gotta really read this carefully. -7. Now I do care about you simplifying this because this can be a multiple choice question on an AP exam. What's that gonna be? It's too early in the morning to just come out of my head. -160, -176. Yeah.
Yeah.
Right. Are you right? Yeah. Yeah, I got that.
Oh, so, yeah.
Yeah.
Wait, Mr. How do you know that W is -2 in the bracket thing?
They told me.
But if you know that, why do you even have to do the primes if you know W is -2? Can't you just plug it into the top?
No. W of 5 is -2, not W of X. The output of W is -2 when the input's at 5.
Okay. Wait.
W is not a constant function. W has got some bunch of stuff I have no idea.
Yeah.
W's got a bunch of X's in it. I don't know.
Don't you just have to know it for x equals 5?
Exactly right. Just the output. That's it. Exactly.
But wait, how do you know that's when it's 5? Because the 5's on the outside?
No, because you're told to do this at X equals 5.
Oh.
We're told to do that at 5.
Sounds good. Yeah.
That's why. We're told to find the derivative of X equals 5. You're overthinking it.
Okay.
Yeah, you well, all we're doing is we're doing the derivative of this and plugging 5, but the things you're already told what those values are.
Sure.
Right.
So if it was like, could the same thing happen, but instead of them giving you like at x equals 5, you could just put functions?
Right. Let me
Derivative functions.
wait, sorry, say again.
like, instead of having it x equals 5, could you have this question, but they give you like the derivative function?
Of course, sure, right. Okay, last one, and then we'll do the quiz. This will be W prime U minus W U prime over U squared. What's W prime? That's 3. What's U straight up? That's 10. What's W straight up? That's -2. U prime is -1. U squared, that's 10 squared. That's 30. Ooh, lots of negatives, but still -2. So you should get 28 out of 100. You can leave it like that. You don't have to reduce it. Would be 7 out of 25 if you did reduce it. So yeah.
All right.
So it kind of forces the issue of the product rule or quotient rule, sorry. I'm not gonna we'll just finish this off on Friday. And then looking at what we're doing tomorrow as well. We'll see how far we get with the linear motion. I don't know. We'll see how far. I'm not doing a quiz tomorrow, so maybe we can get all this done by tomorrow. Let's do the quiz. All right, so I'm all done. So hopefully it makes sense what we did today. Homework is just gonna be handout D, but not all of handout D. It's gonna be 1, 5, and 6 of handout D. And there's gonna be some textbook problems. I'm gonna assign textbook problems, but I made a copy of the textbook though. I made a photocopy of the textbook. It's here. I'll tell you which problems to do. So I'll put in Schoology, do these problems, and the solution key will be in Schoology as well. So, all right. So I'm all done. So.